All right, last section of the unit. And what are we going to do? More applications, of course, because that's the best part of, well, that's not true. I was going to say it's the best part of math, but everything about math is the best part about math. Okay, first problem. This is a doozy. Like, doozy. This one's going to be tough. But with that said, you can do this. I have faith in you. So that's what I'm going to let you try. So we've got a sector with a central angle theta is cut from a circle of radius 12 inches. The edges of the sector are brought together to form a cone. Find the magnitude of theta, which is just saying find the size of theta, so that the volume of the cone is a maximum. So just so that we're all on the same page, picture what's happening. So you have, and even maybe do this, like think about if you took a paper plate, you have one around you. I'm sure everybody just has paper plates sitting around, and cut out a sector from that paper plate. And then the two edges that are formed from the gap of the sector, if you connect those together, the paper plate should now become a cone. That's what's happening in this problem. So we're trying to figure out what angle should we cut out to maximize the volume of the cone. I'll give you a hint. Obviously, you're going to use the volume equation of a cone since that is what we're trying to maximize. Remember, optimization problems, we need to figure out what we're trying to maximize or minimize. Here we're trying to maximize volume. What other things are you going to need? Well, you are also going to need the area of a sector, the lateral area of a sector, and the area of a circle. All of those equations can easily be found on the interwebs or in the front cover of your book. There are some nice relationships between the lateral area, the lateral area of the cone, the area of the circle, and the area of the sector. That's my big hint for how you can put this all together. Pause the video, try this, you got it, unpause when you're ready to check. Okay, so here we end up with the maximum volume of the cone will be when theta is 1.153 radians. Is that what you got? Hopefully. How do we get that? A lot of work. A lot of work. Okay, so this is kind of some of the stuff I was talking about. So I have my circle, right? And I'm going to cut out a sector from the circle. The area of a sector is theta r squared over 2. Okay, that r is a constant. That's 12. The area of a circle is pi r squared. That r is also a constant. That's 12. The lateral surface area of a cone is pi r times the square root of r squared plus h squared. This r is not the same as these r's. So these two r's are constants because the area of this circle is fixed. The area of the sector is not because theta can change. The volume of a cone is 1/3 pi r squared h. This r is also not a constant. This r is the same as the r in the lateral surface area equation. So this r comes into play when I draw the cone. So the cone has some radius, some height, and then the lateral edge of the cone is 12. Because again, that would be from these edges, right? So that is fixed. So if I take my volume equation, I want to get rid of h. I want to just work in terms of r. I know that r squared plus h squared is 144. So h is going to be the square root of 144 minus r squared. So my volume equation becomes 1/3 pi r squared times the square root of 144 minus r squared. Okay, back up here real quick. I want to point out, again, the relationship between this lateral surface area, the area of the sector, and the area of the circle. Notice that this whole thing is the circle, but that this stuff that I shaded in green, that is what is going to end up being the lateral surface area of the cone. Because as soon as I cut out the circle and then fold this together, now that becomes the lateral surface area. So the big relationship that I tried to emphasize beforehand, and that we're going to look at later on once we find the maximum volume, is the fact that the lateral surface area plus the area of the sector equals the area of the circle. Okay, back down here though. We have our volume equation. Let's take the derivative. dv dr, use the product rule, derivative of the first, so 2/3 pi r times the second, square root of 144 minus r squared, plus the first, 1/3 pi r squared, times the derivative of the second, don't forget the chain rule, 1/2 144 negative r squared to the negative 1/2 times negative 2r. Simplify a little bit. Let's get a common denominator, combine like terms, factor out any greatest common factors. So we end up with dv dr is pi r times 96 minus r squared over the square root of 144 minus r squared. Set the numerator and denominator equal to 0 to find our critical values. So we end up with r equals 0, plus or minus 4 root 6, and plus or minus 12 as the possible critical values. However, in terms of applications of the problem, I know that, again, this is the r we're referring to. R can't be 12 because then I don't have a cone. R can't be 0 because then I don't have a cone. And R also can't be negative because it's representing a distance. So I'm going to eliminate 0, negative 4 root 6, and plus or minus 12 because those are not going to be within the domain of the application of the problem. So I can test 4 root 6 using my first derivative test on my increasing decreasing chart. Plug in 8, plug in 10, I get positive, negative. So since dv dr is greater than 0 on 0 to 4 root 6, and dv dr is less than 0 on 4 root 6 to 12, at r equals 4 root 6 will be a max volume. Fantastic. But how does that relate to theta? Great. That's what we still need to work on, right? So now I'm going to use this r to find the lateral surface area. So the lateral surface area, remember, that's where this came in up here, is pi r times the square root of r squared plus h squared. So these r's are the r's from the cone. And I know, remember, h is the square root of 144 minus r squared. So back down here, I can plug in 4 root 6 everywhere that there was an r, and I end up with that the lateral surface area is 48 root 6 times pi. The area of the circle is 144 pi, and the area of the sector is 72 theta. So remember, I talked about up top that the area of the sector plus the lateral surface area had to equal the area of the circle. So I'm going to take this relationship here and I'm going to subtract the lateral surface area so that I can isolate theta. So I know 72 theta has to equal the area of the circle minus the lateral surface area. So 72 theta equals 144 pi minus 48 root 6 pi. Divide by 72. So theta is 144 pi minus 48 root 6 pi, all divided by 72. Or 1.153 radians. So the maximum volume of the cone will be when theta is 1.153 radians. Told you that was a doozy. Next one. Let's move to related rates. This one's a little bit more straightforward. An airplane flying at 450 kilometers an hour at a constant altitude of 5 kilometers is approaching a camera mounted on the ground. Let theta be the angle of elevation above the ground at which the camera is pointed. When theta equals pi thirds, how fast does the camera have to rotate in order to keep the plane in view? Pause the video, try this, unpause when you're ready to check. All right, so here we should end up with the camera will have to rotate at 67.5 radians per hour to keep the plane in view. That is really quick, because this is in radians. And remember, it has to be when we're doing trig derivatives, okay? So how do I come up with that? So, okay, I know that the plane is approaching, so I drew a picture. Here's the camera right down here. I call this Z, I call this Y, I call this X. Here's theta. I know dx dt is 450 kilometers an hour, and I know dy dt is 0 because this is a constant. It's the altitude of the plane. So I use tangent. You can use cotangent as well. The tangent of theta is y over x, which is actually just 5 over x. Also, off to the side, I figured out when theta is pi thirds, what does x actually equal? Well, I know that the tangent of pi thirds is root 3, so if I say root 3 equals 5 over x, then I end up with x equals 5 root 3 over 3 kilometers. I rationalize this. You don't have to. It's up to you. So now I have tangent of theta equals 5 over x. Let's take the derivative. The derivative of tangent of theta, remember on related rates problems, we're always doing the derivative with respect to time. So this becomes secant squared theta times the derivative of the inside, which is d theta dt, equals negative 5 over x squared dx dt. So I'm solving for d theta dt. So if I isolate that, I can divide by secant squared theta, and I can plug in the values that I know. So I know x is 5 root 3 over 3, so I plug that in to the x squared. Secant of pi thirds is just going to be 2, because remember secant is the reciprocal of cosine. Cosine is the x value on the unit circle. The x coordinate of pi thirds is 1/2. So if I type all this into my calculator, I end up with negative 67.5 radians per hour. Now the negative is okay, it just, again, it has to do with direction. So we're just talking about rotation, so I don't care. So the camera will have to rotate at 67.5 radians per hour to keep the plane in view. Again, down here real quick, this is just if you used cotangent. It's very similar. The derivative is actually a little bit easier because you end up with cotangent theta is x over y, which is just x over 5. So the derivative is just 1/5 dx dt, and on this side it's negative cosecant squared theta d theta dt. But either way, you should get the same answer. Okay, so we want to remember that with optimization and related rates, we want to try and get everything in terms of one variable if possible. With optimization, we need to make sure to find our critical values and test to see if they are maximums or minimums. With related rates, remember you are always taking the derivative with respect to time, so everything is implicit differentiation.